In the course of Concrete Structures, Lecture 2, Design Loads and Load Combinations. In every engineering discipline, there are design codes and specifications. Similarly, in concrete structures, there are codes and specifications. Why these specifications needed? These are rules given by various organizations in order to guide the designers for safe and economical design of structures. These are basically guidelines for the designers to make the design economical and to perform well in the loading zones, in the seismic areas, in the wind areas. So to perform the buildings in these all areas well, so we need to follow the design codes and specifications given by different organizations. Here are various codes of practice which used for the design of concrete structures. First and foremost, ACI 31819 by definitely after 3 years or 4 years they repeat the code with changes. ACI American Concrete Institute 31819 by American Concrete Institute for general concrete constructions buildings. HTO, that is mainly for bridges. HTO specification for concrete bridges by American, it's the abbreviation, by American Association of State Highway and Transportation Officials. Third one is ASTM, that is very much common. That is also very common in electrical, mechanical, in civil. Its abbreviation is American Standards for Testing and Materials, that is used for testing of materials for cement, concrete, aggregate, fine aggregate, coarse aggregate. Almost every standard is present in the ASTM for testing of material. Fourth one is the ASC 7, that is American Society of Civil Engineers Code, that is for loads, for example, how much live load you needed, and the design criteria of buildings, that is the ASC 7. Design loads and load patterns, these are same things. For example, if we going to design any member, then we need to design that member against loadings. So in that case, to consider the loading, we need to consider how much or how many types of loading will become to that structure. For example, if the dead load means the self weight of the building, live load if any person or any living thing, any machinery loading is coming, any wind loads, any earthquake loads, then all the loads will come under the design loads. Okay, for example, here I have discussed briefly two loads, dead load and live load. First one is the dead load. The dead load, the load which do not change their magnitude and position with respect to time within the life of structure. For example, beams that will remain its own position for lifetime. They do not change its position or its magnitude. Okay, so the weight of the beam will remain same. Similarly, for column, for slab, for staircase, for all these elements, these are dead loads. Now there is small difference between dead load and superimposed load. Here is dead load mainly consists of superimposed loads and self load of structure. What is self load and superimposed load? Self load, it is the load of structural member due to its own weight. Here is column, beam, slab, column, again footing. For example, this column has its own weight, that is self weight of this member. Similarly, beam it has its own weight, so that is self weight of the beam. Slab has its own also weight, so that's why it's the self weight of the slab. Okay, so now the second is the superimposed load. It is the load supported by a structural member. For instance, self weight of the column is self load, and the load of beam and slab over it is the superimposed load. For example, the column on weight, that is the self load. Okay, the load coming from the slab, beams to the column, so these all loads are the superimposed load. Okay, the load coming on that column, that are superimposed load. Okay, that's the difference between the self load and the superimposed load. Now the live load. Live load, that load will change its magnitude, its occupancy with respect to position. Live load consists chiefly of occupancy loads in buildings and traffic loads on bridges. On the bridges, we consider the live load, that is the traffic that is moving. Okay, and in the buildings, we mostly consider the furniture, some machinery loading, and persons loading, human being moving loading. So these all loadings come under the live load. Their magnitude and distribution at any given time are uncertain. For example, if you design a classroom for certain loading, it does not mean the all students will come at the same time. Some students come earlier and some students come later, and maybe at some time they complete the hall. Okay, so their magnitude, maximum or minimum, are uncertain, and even their maximum intensities throughout the lifetime of the structure are not known with precision. Okay, so there is variation, but codes have given us the guidelines. So what are these? Let's see. Values of live load are specified in the codes. First of all, density of some important materials, for example, PCC, plain cement concrete, that is the 2300 kg per meter cube. Similarly, RCC, reinforced cement concrete, 2400 kg per meter cube. Why I am discussing? Because these important values are needed for the design of concrete structures. Brick masonry, 900 to 930, and 1930, earth, sand, brick ballast, 600 to 1800 kg per meter cube. These are very brief, limited values. Okay, okay, or limited table. So here is a table from concrete structures by Zahid Ahmed Siddiqui. Here is a material, plain material mean PCC. Here is the density, concrete, okay, loose aggregate, okay, glass, steel, copper, bronze, aluminium, lead. Okay, the table is continuing. Brickwork. So all the densities are here. Okay, so in the slides only I have discussed the brief table, so you can see the large table. Now the intensities of live load, here I have discussed their magnitude are uncertain, but codes have given us the values. Okay, for example, you are going to design the residential building, how much live load you needed. For commercial building, for hospital building, okay, so for all these types of buildings, what type, how much magnitude you needed for live load. So here, if you are going to design a residential house or classroom, then you can use the live load 200 kg per meter square. Similarly, for offices, library reading room, library stack room, 730 kg per meter square. Warehouses and heavy storage, 1200 kg per meter square. Okay, again, in the slides I have discussed only the few values, but you can see here is typical minimum uniformly designed loaded values. Here, private apartments, okay, 200 kg per meter square, and the PS, that is 40 PSF, pound per square feet. Library stack room, even in the book that the author have used the some lesser values. Okay, so to see the full form of the table, you can see in the ASE 716 table. Here on the page number 14, you can see in the apartment, corridors, okay, hospitals, libraries, manufacturing, office buildings, okay, that you can see there is large table. Schools, okay, storage warehouses. So the large table or the detailed table of live loads is given in the ASC 716. Okay, you can use that. Okay, now the basic design equation for the design of members. So basic design of equation, that is, for example, if you are going to design any member, for example, you are going to design a beam, okay, a beam element, then the beam have its maximum internal resistance. Let's suppose it's the maximum capacity is 100 kilonewton, that the beam can bear 100 kilonewton. So but you, when you will design the member, then you will not design the member exactly for 100 kilonewton. Okay, for example, if you have a loading of 40 kilonewton that will come uh, on this beam, then you will amplify the load. Why? To accommodate the uncertainties. For example, if by chance there is some more magnitude load, so that load will come in the factor of safety. You will use 40 and to multiply with 1.2, then the load will be 60, and still that will be less than the maximum internal resistance of the beam. So that's the basic design philosophy of any member. Okay, you will apply the factor of safety, or its factor of safety should be less than the 100. Okay, so whatsoever you multiply the factor of safety, it should be less than the value of 100. So that's the factor of safety. So how to calculate the factor of safety? Here, maximum failure load, maximum capacity uh, of this beam. Okay, then the maximum service load that will come, you will get the factor of safety. Okay, you can this factor of safety for any values. Okay, the following points are relevant to factor of safety. It is used to cover uncertainties due to applied loads. For example, if you are going to design a 40, by chance there will be load of 60, but you have used the factor of safety, then you will be on the safer side. Material strength, if there is you have used a 30 megapascal concrete, but by chance due to uncertainties at some, due to labor, poor workmanship, or due to some reasons, the material didn't get its full strength. So to accommodate that abnormality, the factor of safety will come into action. Then the poor workmanship, labor didn't perform the work well. So if there is an errors, definitely the factor of safety will cover also that. Unexpected behavior of structure, we have a perception or analysis techniques, but due to some unnatural reasons, the structure didn't perform the right way as we have expected. So if there is any unexpected behavior, then the factor of safety will also cover. Fabrication during erection of beams, columns, if there is again the issues of verticality, horizontal members. Okay, so these fabrication issues, so that will also cover in the factor of safety. If factor of safety is provided, then at service loads, deflection and cracks are within the limits. Okay, if we have used the factor of safety, then deflections and cracks will be within the limits. It also covers the natural disasters. Now, the ultimate strength design and LRFD method. In the present era and in the ACI codes, the the method which we use for the designing of members, beams, columns, and slabs, that is the ultimate strength design technique, or the LRFD, load resistance factor design method. Okay, what is that? In that, for example, in this strength design method, the philosophy is that we use the factor of safety in such a way that bigger part of factor of safety is applied on loads and smaller factor of safety is applied on the material. Okay, here we use two factor of safety, one factor of safety for applied loads, one factor of safety for materials. Okay, and the bigger part is applied on the loads and the lesser part of factor of safety applied on the material. That is the technique of the ultimate strength design approach. Before the ultimate strength design approach, there is the ASD, allowable strength design. Here is again, that is the same equation of ultimate strength design. Here this left part is named as U, the right part is named as phi S. Okay, 5SN. U is the resultant after coming by applying the factor of safety. Applied load multiplied by factor of safety will be equal to U. Here, required strength calculated by applying load factors. Okay, the right side is material strength multiplied by factor of safety. Okay, here is a nominal strength or the material strength, that is then the factor of safety. Here is the strength reduction factor, that is factor of safety. multiplied with strength or material resistance. This is the right side part. Okay, the right side part should be greater than or equal to left side part, means the material strength should be greater than applied load. Okay, so here so in our members mainly three forces are there: axial, shear and moment. So our axial capacity should be greater than, so our axial capacity should be greater than applied axial load. So our so our shear capacity should be greater than applied shear. So our moment capacity should be greater than applied moment. So that's how ultimate strength design technique work. Okay, now what was the ASD method, allowable strength design? In allowable strength design, the whole factor of safety is applied on the material side, and the service loads are taken as it is unfactored. Okay, so on the load side we do not apply the factor of safety, we apply the factor of safety on the material side. That was the approach of ASD, but now this approach is not, but in some old books that is also present. So that's why I'm discussing here ASD. What is ASD? In both allowable strength design and ultimate strength design, analysis carried out in the elastic range, means all the values of material are used in the elastic range. For example, here is steel, here is the yield, and here is the ultimate. We use in the design, the values are under the elastic limit, under the yield point. Similarly for concrete. Okay, so that's how we use the allowable strength design. Okay, steel, concrete, that is stress strain curve of concrete, that is the stress strain curve of steel. Why that is Fy by 2, Fc prime over 2. Fc prime is the ultimate strength of concrete. That is showing the allowable strength design technique. The material, the factor is applied on the material side. For example, if we are designing member, then we use the concrete strength half. Similarly for steel, we use the strength of steel half, the yield point divided by 2. That is the approach of the allowable strength. We do not apply the factors on the service loads. The plastic design, that is the advanced design technique. In the plastic design, plastic analysis is carried out in order to find the behavior of structure near collapse. We go in the inelastic range, means here is the elastic range, here is the plastic range. We go in the plastic range and determine what type of the failure of the structure. To study that behavior, we perform plastic design technique. In the plastic design, plastic analysis is carried out in order to find the behavior of structure near collapse state. Okay, near the failure point, we study the behaviors of the structure. In this type of design, material strength is taken from inelastic range, means we study in the inelastic range. It is observed that that is our observation after the plastic design, that whether this failure is sudden or ductile. Ductile failure is most favorable because it gives warning before failure of the structure. We try to design or maximum emphasize on the design, that design should be ductile. Why ductile? Because if we have a ductile structure, if any structure is going to fail, then there will be failure warning, means structure will deform, maximum cracking will appear, then the occupants can evacuate from that space easily because there will be failure. So it's the warning before failure appears in the ductile structures. Okay, we want the ductile failure, that comes in the plastic design. The basic objectives of the designer, there are two basic objectives of the designer, that is first one and the foremost, that is safety, and after that, that is economy. We try to use the materials that is cheaper and easily available in the market. Now the load combinations, there are basically two things I have discussed in the LRFD design method. One is the factor of safety, which we apply on the loads, and the second factor of safety which we apply on the material side. So what type of factor of safety we use on the load side, that are here 1.4 dead, 1.2 dead plus 1.6 live. Dead means dead load, L mean live load, LR mean here live load on roof. Okay, why the live load is different for lower stories and for the roof. For roof, we do not use as an normal in normal routine, so that's why it's live load is reduced. Okay, it is wind load. Okay, when these load combination come into active, if you are going to use only dead load, so you will use only one load combination, 1.4 dead. And if you are using dead and live, then you will use the second load combination, dead and live. Okay, and if you are using a roof load also, then dead, live and roof load. And if you are using a wind load, then 1.2 dead plus 1.6 live and plus 0.8 wind or 1 live. Again, these are few examples of load combinations. The full list in the codes here. Here, I have already told you the result after applying the factor of safety on the loads, 1.4 dead. Similarly, if there is a wind, you can use the combination 0.9d plus 1 wind, and for earthquake 0.9d plus 1 earthquake. So these are the load combinations which we apply on the load side. Okay, so what factors we apply on the material side? So these are the factor of safety for the material side. Strength reduction factors and resistance factors. For the tension control members, what are tension control, compression control? Okay, that we will discuss in our next lectures. So for tension control sections, mean for bending or flexure design, we use the factor of safety 0.9. For the compression control, there are two further types: columns with ties, column with spirals. If we use column with ties, then that will be 0.65, and with spirals that will be 0.75. Okay, and if we are going to design our member against shear and torsion, then we will use the strength reduction factor 0.75. So that's all for design load and design load combinations. Have a nice day.